Hello student, today we are going to study one simple concept, namely conditionally convergent. So first we see the definition of this concept. So a series summation an is said to be conditionally convergent if it is convergent but not absolutely convergent. So one series summation an is convergent, but summation modulus of an is not convergent, then the series is known as conditionally convergent series. So this is the definition for this conditionally convergent topic. Let us see one example. So we are considering the series summation minus 1 the whole power n by n. So obviously this is one alternating series. So to test the convergence of alternating series, the basic test is Lebanon's test. So for this Lebanon's test we have to consider two conditions. One is an should be a monotonic decreasing sequence. So an should be monotonic decreasing and limit n tends to infinity an equal to 0. So if these two conditions are satisfied, then by Leibniz's test the alternating series must be a convergent series. So clearly our an value is here 1 by n. Obviously this 1 by n sequence is a monotonic decreasing sequence, and limit n tends to infinity 1 by n is also equal to 0. So by Lebanon's test we can conclude this series is a convergent series. So now we are going to tell this is not absolutely convergent. So for that we are considering summation modulus of minus 1 the whole power n by n. Obviously this value is summation 1 by n. So we know this is a harmonic series with p equal to 1, and so this series is divergent, and hence summation modulus of minus 1 the whole power n by n is also a divergent series. Therefore summation minus 1 the whole power n by n is not absolutely convergent. So the series is convergent, but this series is not absolutely convergent, and so by definition of conditionally convergent, the given series summation minus 1 the whole power n by n is conditionally convergent. So this is one simple example. So we are going to solve one problem under this topic. So here our problem is like this. So we are given with one series, that is alternating series, and we have to prove that series is conditionally convergent. So we have to check two conditions. One is the given series should be convergent, and another one is it is not absolutely convergent. So that two items we have to prove here. So our given series is alternating series. We know the notation for alternating series is summation minus 1 the whole power n an, so which is equal to your given term. So comparing these two, we can write our an is nothing but root of n squared plus 1 minus n. So this is one irrational term. So we can multiply this one by its conjugate. So multiplying the numerator and denominator by the conjugate of this term, we will get the term an is equal to 1 by root n squared plus 1 plus n. Okay, so next from this we can write our an plus 1 is this term, that is in an we are replacing n by n plus 1, then we get our an plus 1 term is like this. Now obviously this n squared plus 1 root of n squared plus 1 plus n, and root of n plus 1 the whole squared plus 1 plus n n plus 1. So these two terms are compared. So obviously this term should be less than root of n plus 1 the whole square plus 1 plus n plus 1. So you can check with some values. So from this we can conclude reciprocal of this term are greater values. So we have an is greater than an plus 1 for all n. Therefore this an is a monotonic decreasing sequence. So to apply our Lebanon's test, we need one more term. So for that we are considering limit n tends to infinity an value, which is limit n tends to infinity. Here we know our an is nothing but 1 divided by root of n squared plus 1 plus n. Okay, so that term is taken here, and applying n is infinity we get this value equal to 0. So in our alternating series, that an is a monotonic decreasing sequence and limit n tends to infinity an value is 0. Therefore by Leibniz's test, the alternating series summation minus 1 the whole power n root of n squared plus 1 minus n is a convergent series. So to prove the given series is conditionally convergent, it is enough to prove the given series is not absolutely convergent. So you have to prove not absolutely convergent means you have to consider modulus of the given term. So I am considering modulus of minus 1 the whole power n root of the n squared plus 1 minus n. So this modulus value is here taken as some an. So obviously modulus of this value is only we get root of n squared plus 1 minus n. Again by multiplying numerator and denominator by conjugate as we did in the previous concept, we will get our an is 1 divided by root of n square plus 1 plus n. Okay, so to check the convergency we are going to take one term. It is denoted as bn. I am taking bn value is 1 by n. Then our an divided by bn is nothing but 1 divided by root of 1 plus 1 by n squared plus 1. Okay, so we are taking n from our denominator and cancelling we get this term. Okay, so now applying limit for this, we will get limit n tends to infinity an by bn, that value equal to 1 divided by, here we get 1 1 and here also we have 1, so totally we have 1 by 2. So this value is obviously more than 0. So we also our bn value is 1 by n. Therefore summation of bn which is nothing but summation 1 by n. So we know this series is a divergent series. So now we are going to apply the comparison test. So comparison test is nothing but if one series summation dn diverges and limit n tends to infinity an divided by dn exists and that value is greater than 0, then the series summation an is also diverges. So that is our comparison test. So here also our series summation bn is divergent and limit n tends to infinity an divided by bn value is exist and that value is greater than 0 also. So by comparison test summation an is also a divergent series. So an is nothing but summation modulus of minus 1 the whole power n root of n squared plus 1 minus n. Therefore that series is a divergent series. That means our series summation minus 1 the whole power n root of n squared plus 1 minus n that one is not absolutely convergent, but previously we proved this series is convergent. Now we proved this series is not absolutely convergent. Hence, by definition, we can conclude our given series is conditionally convergent. So this is one simple problem under this topic.